here. So, no one's feeling talkative today. Damn, I don't have Joe today. God damn. So how's everyone been? Alright, all good, all good, all good. Good to hear.
That's fun, right?
So, yesterday we covered the basics behind organic, which should just be. Thanks, Daniel. Yesterday we covered the basics behind organic. Uh, Today we're gonna be focusing more onto we're gonna be focusing more on just the organic pathways, which is the thing they're going to test you on. I guarantee you, your exam will have an organic pathways question, and if you get really good at this, you can finish this question in like 5 minutes, like max. It'll be like maybe it might be a 5 to 7 mark question. You can probably finish it like actually even less than 5 minutes. You can probably finish in like 2 to 3 minutes if you know your pathways really well. Yeah. So just need to check something before I continue. Everything is here. Okay. So I'm just worried I'm missing something. So we'll start on. So I'm gonna show this definition slide each time. You're not required again to know any of these specific definitions. They're more or less a nice to know than need to know. I think the only one here that you really need to know is maybe like what an enzyme is, because everything else will more or less be covered in the idea. You just need to be able to look at this and you either need to be able to see the name and identify what you're thinking about, or you need to be able to well, so you either need to look at the name and identify what you're looking at, or you need to be able to like told, okay, this is a fatty acid, right? What is a fatty acid? Now, a lot of these things you need your best friend for. So who here has their best friend? Put your thumbs up. You got your best friend next to you. And if you don't know what that is, I'll be very disappointed. All of okay, okay. All right, good. We got these two got their best friends. All right. Oh, okay, bro. God forbid. Anyway, everyone, you have to have your data book for this one. It's simply a must. Uh, yes, Emeth, is it anything you want to ask? Or are you just saying you have your data book here? No, I got mine. Okay, sure. So, again, on this page, there's nothing you really need to know here. Again, we'll cover. Okay, so it's just remember this is being recorded, so be mindful. I think the only thing you really need to know here is the idea of what metabolism is, right? It's the process in which your body creates energy from food. So just remember that. But we'll deal with all of these different phrases once we get to them. So our first organic pathway. I'm gonna assume that you guys remember your your organic, yeah. And the first part of this path, the first pathway that we learn about is the alkene reacting with a halogen, yeah. So here they've just chosen bromine. They've chosen bromine and ethane, yeah. So we have an alkene reacting with a halogen, which produces a haloalkene, yeah. So here they produce bromoethane, and then over here, right? So and over here we're producing hydrogen bromide, and this is a substitution reaction. You can think of the hydrogen over here in this ethane is being substituted for the bromine over here. They're switching places. They're substituting. So now we have the bromine over here. We have the hydrogen over here, and that's what makes it a substitution reaction. Yeah, it's that we're switching two things. So I want you to remember that substitution is switching. Yeah. So one thing is switching to another. And the thing that you need to remember here is you need to remember that the general formula, which is the alkane plus the halogen produces a haloalkane, plus like a hydrohalogen, right? So here the hydrohalogen is just bromide, yeah? You need to remember this general formula as well as the fact that here the catalyst is UV light. So you need ultraviolet light, and you just represent that by showing at the top of the arrow that this is UV light reacting here. So any questions about that at all? No, everyone's gonna give me thumbs up if that's all good. Yep. Couple thumbs up, thumbs up all around. Yep. Okay. So now we move on to the substitution reaction. The substitution one. The substitution one is very similar. Yeah. Here, right, we start off with a haloalkene, right? So haloalkene, and they use the phrase primary haloalkene. We only generally deal with primary haloalkenes, yeah. But here we have a haloalkene, right? And it's added to some hydroxide, right? So this could be that here they choose sodium hydroxide. It could be potassium hydroxide. It could just be hydroxide by itself, yeah? So it could be any of those things. And when we react these two together, what's going to happen is we're going to produce ethanol, right? Essentially what's happening is this bromine and the ethanol are switching places. So here, right, the bromine is switching places with this hydroxide group, and the hydroxide group is taking the place of that ethanol. And here, now we're left with this new compound. Now, depending on what we had over here, if we had sodium, we produce sodium bromide. If we had here potassium, we'd expect potassium bromide. Or if it was just OH, you just expect bromide to be flowing by itself. Yeah? So any questions about that? And the big thing here that you want to realize is this produces a primary alcohol, because this is a primary haloalkene. Does everyone here remember what the phrase primary means? Just put your thumbs up if you remember what primary means. Thumbs down if you don't. But I'll explain it anyway. Okay, yeah, everyone. Yeah. So here, yeah. So everyone remembers that idea of the primary. Essentially, it's only bonded to 1 or 0 carbons. Yeah. Here, this hydroxyl group is bonded to only one other carbon, right, besides its main carbon. So its main carbon is only bonded to one other. So, any questions about that? So that's our second type of substitution. Okay. Nothing. I'll move on then. Here, right, with this one, this is another type of substitution. Yeah. Instead, it's basically the same thing. It will produce the same thing as not the same thing as our previous one, but this is a new one on the study design. Personally, I haven't it never came up on my exam. I haven't seen it on any past exams, but it's again a haloalkene, and again they use a primary haloalkene reacting with water produces ethanol and hydrogen bromide. So you can think about it as haloalkene plus water produces alkanol, right? So that's just a alkene that's an alcohol, yeah? And then hydrogen bromide. And this is another type of substitution, yeah? Or hydrohalogen. I'm going to use X, right? Remember, X represents a halogen, yeah? So I'm going to use X here, but essentially what's happening is the halogen over here is substituting with this hydroxyl group, right? And we're producing these two compounds. Does that make sense to everyone? Give me a thumbs up. So I've seen a couple similar faces. Emeth, yeah. What about you, Daniel? What about you, Blessing? How you finding everything so far? Yep. Up, thumbs up. Okay. So this one's also new, yeah. And this is a two-step reaction, yeah. So essentially, right, we have two separate reactions which sort of go, okay. We have more people joining. Hello there. I'm just gonna keep I'm gonna just keep going on. If you guys have missed anything, it's all in the recording. Yeah. My thumbs don't exist. Okay. So now what the If you guys want to see any of the previous stuff, it's in the recording. I'll post that. I'll post that online. It's on the YouTube channel. So the big thing that you want to recognize here is that this is a two-step. This is what we call a two-step reaction. Now, I think this is called like ammonitization, or like, you don't really need to know the name of this one, but this is another type. So everyone can see my screen share again. Okay. So we'll keep going on with this one. Yeah. So here, right, we have a two-step reaction going on. Essentially, ammonia is reacting with, again, a haloalkene. So a lot of these require haloalkene reaction. Yeah. Might want to restart that recording. No, the recording's still going. But it's live, so I can't really do anything about it, and I'm gonna have to take down that live stream. So I'm gonna have to take down the live stream and fix it up. So let me just, yeah, I'll fix it. I'll fix it in a bit, but I'm gonna have to fix that whole thing. That's actually really annoying. But we have just a halogen reacting with an ammonia, right? And that produces an ammonia salt. Again, what's happening? Essentially, what's happening here is this is being added onto it. Yeah. So this whole ammonia is just being added on to produce this ammonium salt. Yeah. Then afterwards, the ammonium salt again reacts with ammonia to then produce this amide. And here what's happening is you can think about it as we're sort of substituting, right, the NH2 part of this, right? So only NH2 into this, and this part over here bonds to that singular H that's left behind, right? So that's what's left over there. Does that make sense to everyone? Does anyone have any questions about that? Okay, because this is a new one, and I haven't seen many schools really teach this one. It's on the thumbs up from everyone. Is that all good? Just gonna confirm. Sorry about that interruption, guys. So, okay, now this is the last type of substitution that we deal with, and this substitution is again another new one that you guys wouldn't have seen. Here it uses an I've never been able to pronounce this. Again, it's just an aluminum trioxide catalyst here to catalyze the reaction. But here you can think about it as just an alcohol. Alcohol reacts with ammonia, right, to produce an amine, right? So you can think of this whole group is substituting with the alcohol, and the hydroxyl group is just becoming a new water molecule. Does that make sense to everyone? So those are the different types of substitution reactions here. Again, you need to know this catalyst, right? You cannot do this without knowing the catalyst. If you don't know the catalyst, that's where a lot of the quick marks come from. So is that all good? Give me thumbs up, guys. Give me the thumbs up. Is that all chilly? Okay. Perfect. So here, which of the following equations shows the combined reaction for the stages involved in the formation of an ethyl amine? Right. So which one of these shows the combined equation for the formation of ethyl amine? So which one of these is the combined equation to form the ethyl amine? Who thinks it's A? Give me thumbs up if you think it's A. Or just type your answers in the chat if you want to do that instead. Is it A, B, C, or D? Type your answer in the chat. So C, okay. Any other C? We're getting a lot of C's. C. Okay, I'm seeing C a lot. So it's talking about the combined two-step. The answer is actually D, yeah? Here, it's looking at this reaction, yeah, and it's combining the two steps of this reaction into one, yeah. So here we have the bromoethane plus the two ammonia actually produces these two reactants here. So the answer here is actually D. Does that make sense to everyone? So we're combining those two reactions together. Yeah? Does anyone have any questions about that? Is all thumbs up all around? Explain once more, please. Okay. So here, right? Because in this two-step reaction, we can see that this first part's happening, yeah? And this first part produces the bromide salt, yeah? Do you agree that if I just add another ammonia to this reaction, right? The bromide salt will then immediately react with this ammonia and will produce this amine and this ammonium bromide, yeah? Or ammonium halogen salt. Yeah, okay. Does anyone else have any questions about that? Damn, just getting aired out over here. Breaks my heart. Here, halogens can be used as a reactant to synthesize. Can it only be used for amines? Can it be used only for alcohols, both amines and alcohols, both alkanes and amines? So, which one is it? A, B, C, or D? What do you guys think? Put your answers in the chat. What do you think? A, B, C, or D? Don't be afraid. Okay. C's. Does everyone agree with that? Does everyone think it's answer option C? So it is C, yeah. We haven't actually seen a reaction that produces alkanes. Yeah, we've seen reactions that use alkanes, but we don't see reactions that have produced alkanes. Yeah. So we move on here. So that's that. Those reactions are our substitution reactions. Yeah. Now we're gonna have our addition reactions. Yeah. So we had substitution, and now we have addition. Yeah. Essentially, an addition reaction, how that differs is that instead our basis most of the time, before it was like alkanes and haloalkanes, now it's alkenes. Yeah, it's alkenes that are taking over. Yeah, so alkenes are the thing that are reacting, and depending on the reaction for this one specifically, it is going to be a hydrogen halogen. Yeah, so here they've chosen hydrochloric acid, and we can see that what's happening here is that this double bond breaks between the carbons, and here the hydrogen is going to go on one, and the chloride is going to go on the other to produce a haloalkane. Does that make sense? So I'm using a lot of pictures to demonstrate this. And that's why it's an addition. You're adding it on, yeah? You're adding it on, that's why it's an addition. Does that make sense to everyone? I've seen from Salam. What about anyone else? Yes. What about Emeth, Blessing, Neo? How are you guys? Okay. All good. All good. Okay. So these are types of addition reactions, right? Here we have you. Okay, you don't need to know the name, right? If you were going to write the name on your here, they will accept the answer, just the addition reaction. Yeah. If you do write the name, make sure you do not misspell it. One time, I accidentally misspelt one of these. I lost the mark. It was the dumbest misspelling. They accepted the mark addition, but you don't want to make yeah. Thanks, Cap. Always keeping me humble. So there's different types of the additions, right? They all work in similar ways. So here, right, we have the hydrogenation. which is the addition of a hydrogen to an alkene, yeah? Again, it breaks the double bond and the hydrogens join on, and they produce an alkane. Does that make sense? Alkane. Does that make sense to everyone? So the hydrogens join on after breaking the double bond. And here we need to be mindful, this has a solid nickel catalyst. This one also runs at 150 degrees, but to be honest, they don't test on the temperature that much. If they ask you a question, they might be like suggest why this could be a gas, or suggest this, or suggest that, or suggest why they might need to be careful with hydrogen gas. It's because heat is required here in some way, shape, or form. Yeah. So, does that make sense to everyone? Because down here, the halogenation works in the exact same way, but instead of being a hydrogen, it's a halogen. Yeah. So again, that halogen breaks the double bond. The halogen joins on, yeah? And now we have a dihaloalkane, yeah? So this produces a dihaloalkane. Or in this case, it is dichloroalkane, yeah? And here we need to put the numbers on because technically they're at different positions. So this is on the first carbon, this is on the second carbon. So it needs to be 1, 2, dihaloethane, sorry. Dihaloethane. Does that make sense to anyone? Any questions about that? Any comments, any concerns? Salam's all on top of it. Does it matter where you put adding reagent? Does the state of the catalyst matter? The state of the catalyst does matter. What do you mean by doesn't matter where you put the adding reactant? Oh, yes. So, like here, right? This, like, yeah, I'll just clear this really quickly. Yeah. For this example here, yeah, you can't have you can't have both of the chlorines on the same hydrogen. Yeah. They need to be on different hydrogens. I mean, different carbons. Yeah. They can't be on the same. And like logically that makes sense. I'm breaking the double bond here, and I need to add one more to complete that. Does that answer your question, Emeth? Yeah, okay. So here we also have hydration. Hydration is probably the most interesting one here. It has the most catalysts, yeah? Because here it has this, it's still an alkene, so alkene, but the alkene's reacting with water with a phosphoric acid catalyst. Now this one, it can be liquid. Sometimes they say solid. There are other catalysts they can use for this, but generally they generally like to stick with the phosphoric acid liquid or the phosphoric acid solid. Yeah. And the other things that you want to think about here is that this generally runs at 300 degrees at 60 to 70 atmospheres. Yeah. So this is a very high pressured reaction, right? And I want you to remember that for when we go into sustainability and we're dealing with more of the sustainability principles. But here we can see that the hydroxyl group is being added on, and so is this hydrogen to produce this alcohol here. Yeah. So all the time with these addition reactions, we're just adding it's an alkene, and we're adding those reactants onto the alkene in some way, shape, or form. Yeah. The big thing here isn't really the reaction that you need to remember. It's more or less the catalysts, which a lot of people tend to forget. Yeah, because the reaction themselves are pretty straightforward. Then, so does anyone have any questions about that before I move on? Okay, so no one doesn't have any questions. Okay, give me like a thumbs down if you don't have any questions. Okay. So now here we have the polymerization. Yeah, polymerization is more of a year 11 thing. They don't deal with it too much in year 12. But the idea is that you just have a bunch of these, and you have a bunch of alkenes. Yeah. So here they have ethene. Yeah. And what's happening here is that the double bonds are breaking and they're sort of just joining each other. The double bonds are breaking, they're joining each other, and it forms this polymer, right? Which we call polyethylene, yeah? Now, you don't need to really know this one that well, yeah? It's more or less, I just want you to introduce you to this idea of the polymer, yeah? And here, when we see this N, this means it repeats for N number of times, right? The big thing here when you're showing these ones off, if they show these off, they're probably going to focus more on the amino acids if they're going to do this. But you need to have these side chains, right, just stretching out. They're not connected to anything because it shows that the chain continues, right? Because think about it, these chains, they're basically infinitely long. That's what it's trying to show up here. So does that have any questions? Does anyone have any questions about that one? You don't need to know this one in huge detail because they're going to care more about the year 12 stuff than the year 11 stuff. So just give me a thumbs down if you don't have any questions. Thumbs down. Okay. Is that all good? Perfect. So here, the reaction above is an example of N. Is it a addition, subtraction, substitution, elimination? So which one of these does everyone think this is? What do you guys think it is? We got A, we got A's, we got a couple of people saying A, we got a couple A's. Yes, the answer here is A. Yeah? This is an alkene. Alkenes only undergo addition reactions, right? That's the best way to remember it. Alkenes only undergo addition reactions. They don't undergo any sort of other types. So, if anyone said subtraction or elimination, I'd be kind of disappointed because we haven't even spoken about them before, and we're never going to. So yeah, and like substitution. This isn't a substitution because substitutions happen to haloalkanes and alkanes. Here, which one of the following organic compounds cannot be made by a single step addition reaction with an alkene, right? So a single step, right? That means we only need one reaction, yeah? Which one of these can't be produced by one reaction? Does anyone have any ideas, any thoughts? What do we think? Who's picking answer option A? Who's picking answer option B? Who's picking answer option C? Who's picking answer option D? A. Okay. C. C. Okay. Yep. Does anyone else know? Anyone have three there? Do you guys want to just take a guess? I don't mind. I don't mind guesses. I don't like guesses, but I don't mind guesses. Rose is rage baiting me now. Here the answer option is D. Yeah. This one can be produced by the hydration of a butene. Yeah. This one can be produced by the polymerization of ethene. Yeah. This one can be produced through the hydro. Oh wait, no. The hydrohalogenation of ethene. Yeah. We haven't spoken about any pathway that produces an amine through an addition reaction or through an alkene. Yeah. I was gonna go with D, but dude, bro, this is recorded. Guys are out of pocket. Here, what is the name of the product formed when chlorine? Man, we don't say that. What is the name of the product formed when chlorine Cl reacts with butane 1-ene? Right? What is the product produced? Is it A, B, C, or D? What do you guys think? A. Anyone else? Emeth, Blessing, Daniel, Mia. What do you guys think? Okay. Yeah, so the answer is A. Yeah, I hope you guys aren't just saying A because the other two said A. That we have a 50% we have a 50% pass rate on these multi choice. Yeah, you can think about it as this is butene. Yeah, I'm not going to draw the hydrogens because I'm going to be a bit lazy. But here, if we add the chlorine on, right, what's happening is we're breaking that double bond, right? So we have one of the chlorines go here, right? One of the chlorines go here, C and C, which means it's going to be 1,2 chlorobutane. So is that all chill? Is there any questions about that? Now we have here esterification. Yeah, this is different to trans-esterification, which many of you have heard. Yeah, so all of these reactions that we're looking at right now, or for the next little bit, are condensation reactions. So you don't need to refer to them by their specific names. However, if you're going to spell esterification, please spell it right. Okay. Again, you don't want to lose marks because you spelled it wrong. You have to remind me. So here we have two different reactions here. Yeah. This up here is the condensation reaction. Yeah. And this down here is a hydrolysis. And what you will notice here is that all the condensation and the hydrolysis are reverse reactions of each other. Yeah. So what I'm trying to say here is that all condensation reactions have a reverse counterpart, hydrolysis. Yeah. So here, right, what's happening is that in the condensation reaction, the ethanoic acid loses its OH group and the alcohol loses its H plus group, right? They join together at this oxygen here, right, to form propyl ethanoate. Yeah. So here the alcohol forms the beginning part, the propyl part in this case, and the ethanoate forms that basis of the ester, right? This ester linkage over here. Does that make sense? And then here, what we can see is that the hydrolysis is just the reverse reaction of it, right? Here, condensation polymerization, is that a thing? Yes, it is, but we're not looking at it right now. So we're just looking at basic condensation reactions, yeah? So condensation reactions produce water. That's the big thing you want to remember. And hydrolysis reactions, right, use water, yeah? And they're just reverse reactions of each other. Over here, when they have the ethyl methanoate, yeah, the methanoate gets turned into methanoic acid as this hydroxyl group joins it over here, yeah? The ethanol is going to take this water, the ethyl part is going to take the water and it's going to form ethanol. So does that make sense? Give me some thumbs up if that makes sense. And all condensation and hydrolysis reactions work in the exact same way, right? They all have, if there's a condensation reaction, there's a hydrolysis to match it. So, repeat what I said. So all condensation reactions have a reverse reaction, have a hydrolysis as their reverse reaction. Yeah. And the big thing that I didn't point out over here, I almost forgot it. You need to have this catalyst for it to work. This is sulfuric acid. Yeah. Sulfuric acid. It's liquid sulfuric acid. Or if you want to be extra special, concentrate. It just needs to be a highly concentrated solution of sulfuric acid. And that's what the liquid part states. If it's liquid, it's just pure sulfuric acid. Yeah? The other thing over here, they say X is H plus. This sulfuric acid will show that part off. Yeah? So sulfuric acid is completely, is the only thing you need to remember for this hydrolysis. Yeah? Any questions? Is that all good? So what is ester? Oh, the process up here is esterification. Esterification is the production of an ester. Yes. Just like how trans-esterification is the production of multiple esters. So esterification can be considered to be a subset of which which type of reaction? Hydrolysis, condensation, polymerization, or substitution. So give me an A, give me a B, give me a C, give me a D. I don't know, I was trying to be funny, but okay. B, 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 B. Getting B's all around. Okay. I should probably start using Zoom for this because then I can like put polls up and everything. So here, the equation is an example of what type of reaction? Is it condensation, denaturization, hydrolysis, or addition? So who said C because someone else above them said C? And who said A because someone else above them said A? Because here, right? I misclicked, bro. You type it into your keyboard and click enter. My dog. You don't even have a dog. But yeah, it's not B. We haven't even spoken about it. Denaturization. It's not a type of reaction. Yeah. But here it produces water, right? And it's a condensation. Right? So this one here is a condensation. If it was using water, it'd be a hydrolysis. So, and here to prepare the ester propanol to prepare the ester propanol methanoate, which reagents are used? Propanoic acid and methanol, propanoic acid and ethanol, methanoic acid and propan-1-ol, or methanoic acid and propan-2-ol. What do you guys think? A, B, C, or D? My answer's from A, C. C, C. So here, Salam, I see the mistake you've made, but here the answer is C. Yeah. So here it'd be propanoic acid if this was methyl propanoate. Yeah. If it was methyl propanoate, you'd be absolutely right. Yeah. I don't know why it's C. Yeah. Here, right? This methanoic acid part makes up the actual ester linkage. So the methanoate. Yeah. So here, right, we have this is the methanoic acid. This here is the ethanoic acid. I mean, ethanol. Yeah. What's happening here is that this loses its H, this loses OH, and they connect to each other to produce the methanoic to produce that ester. Does that make sense? So we're literally using this as my basic one. What the difference between C and D? We do not deal. Yeah, one's a primary alcohol, one isn't. That's true. But we only deal with the production of primary esters. Yeah. Or we don't deal with the production of branched ester chains. Right. That's actually a thing on the VCE study design. We only deal with non-branched esters. Yeah. So we have this reaction. This is called an oxidation. Yeah. This is an oxidation reaction. Yeah. Essentially, there's two steps to this, yeah? So this is the oxidation of a primary alcohol. The oxidation of a primary alcohol becomes a aldehyde. And then afterwards, this aldehyde can be further oxidized into methanoic acid, yeah? Now, I just want to put this note down here, right? I put this note down here to show that most of the time, if we have enough, what's going to happen is it's going to go straight over here, yeah? It's going to go methanol straight to methanoic acid. It will just skip this methanol, yeah? But if we have a lot of concentration, it will only partially oxidize. Methanol, is that a typo? No, methanol is a aldehyde, yeah? So that's the naming convention. We use al as the prefix for aldehydes. I mean suffix. Now the big thing that you want to remember here is the reagent. This is called acidified either potassium permanganate or dichromate, yeah? It's either acidified potassium permanganate or acidified dichromate. You can have either one of these as our reagent here, yeah? So you need that, and that will oxidize this from methanol to methanol and methanol to methanoic acid, or methanol straight to methanoic acid, yeah? That's one way we can think about it. So this is technically, so we call this a partial oxidation when it goes from here and here. We call this part a full oxidation. Bro, the spelling's in your data book, bro. It's chill. You don't need to remember how to spell this part. But does that make sense? Thumbs up all around it. Everyone understand that? Do we need? Yes, you need the acidified part. You need to call it acidified potassium permanganate, or acidified permanganate or acidified dichromate. So do I have thumbs up from everyone? So again, oxidation reaction. Usually, most schools will teach you the full oxidation, but I'm going to show you you need to know the partial one as well, yeah? And this is of primary alcohols. Primary alcohols, yeah? This differs from our secondary alcohols, right? So let's just say we had, this is going to be, here, this is propan-2-ol, yeah? If propan-2-ol reacts, what it will become is it will become a ketone, yeah? And the reason being is because it's a secondary alcohol. And this is all it can do, right? It can only undergo a partial oxidation, right? It will only undergo a partial oxidation. It won't oxidize further to produce a carboxylic acid. It will only produce a ketone. So that's a secondary alcohol. They produce ketones, yeah? So here, the ketone the ketone group will be on that second carbon. And tertiary do not oxidize at all, yeah? So no tertiary alcohol will oxidize, yeah? So, repeat. No tertiary alcohol. So tertiary alcohols won't oxidize. Secondary alcohols will oxidize into ketones, yeah? So tertiary alcohols won't oxidize. Secondary alcohols oxidize into ketones and no further. They only partially oxidize. Right? I just wanted to show this one off. We'll discuss this a little bit more when we get to what's the unit called? When we get to analysis and chemical testing, right? This is more or less how can we tell the difference between like what are some other ways? We don't need to know these for the study design, but like think about it. Well, of course, if we put oxygen there, it's gonna get oxidized by oxygen, right? If we have a catalyst there with air, it's going to be oxidized by the oxygen. We'll discuss these ones more though when we get to tests, specific tests, because these are specific tests that we might want to we can discuss. So the process involved in producing a carboxylic acid from an alcohol is referred to as, what is this process referred to as? Is it a substitution, oxidation, reduction, or polymerization? We got B. We got two B's. We got three B's. No more B's. We got a fourth B. Do you have any more B's? Two B. What? Okay. Okay. Oh, what about you, Mia, Blessing? What do you guys think the answer is? A, B, C, or D? B? Okay. It's B here. Yeah. Poll would be better. I should. Man, I'm not made of money like Contour, but I don't have that. Okay, here. In order for oxidizing reagents to function, they must be acidified or in alkaline, must be neutral, change color when oxidized, contain a transition metal. I chose answer option E. Because we greedy. So here, the answer is A. Yeah. We haven't discussed the alkaline part, but think about it. When we do redox chemistry, we either balance cohes in acidic conditions or cohes in basic conditions. Yeah. So you're sort of mixing the two. You're mixing the ideas together. Yeah. You're mixing your ideas from redox and organic, and you're creating this final conclusion. So does that make sense for everyone? I should really get like a pool. I might get like a little website to Oh, I understand it now. Here, what is the systematic name for the product of the reaction of the product of the reaction? Is it 2-methyl pentanoic acid? Is it 4-methyl pentanoic acid? Is it 2-methyl butanoic acid? Or is it 3-methyl butanoic acid? A, B, C, or D? B. B. No, D. So D. What does everyone else think? So D. Maybe that. What do you think, Cav, Blessing, Mia? What do you think the answer is? Okay. It's not pentanoic acid. Nowhere in this chain is this pentanoic acid. Yeah. Here we have C, 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 C. And what's happening here is that this carbon at the end is going to become a 0. Yeah. OH. We get H, 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 C, H, 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 H. Now, the reason why this is D and not C is because the carboxylic acid group is always on the first carbon. Yeah? It's always on the first carbon. Right? So here we're counting it in 1, 2, 3, 4. Yeah? The carboxylic acid is the highest priority group. Remember from yesterday's class, it's the highest priority group. So it's gonna have the highest priority when we're dealing with this, yeah? So it needs to start off at carbon 1. So here that's why it's 3 methyl butanoic acid. So this is a complete table of all the basic organic pathways. We aren't done with organic pathways yet. But these are all the basic organic pathways, yeah? And the Adrolo textbook has been so kind to donate me this image. So, the only one here that you probably don't really need to know is this, but I'm not going to say that because that's if it's going to be the thing that shows up. Watch, it will be like the thing that screws everyone up. Bo had to emphasize basic. No, basic as in we haven't dealt with the large compounds yet, right? We still have amino acid chains, triglycerides, polysaccharides. We haven't looked at any of those, yeah? We've only looked at the very basic fundamental ones that we built up, yeah? We still have a whole heap of others, yeah? So I'm gonna post these slides up. Keep moving. Okay. Have a go at this one. What is the IUPAC name for the product of this reaction? Is it A, B, C, or D? What do you guys think? 2 B's, we have a C. What does everyone else think? You got B, B, C. You're trying to be funny, aren't you? So here, it's B, yeah? It's not gonna be C. Because here, the hydrogen, if it goes over here, red like a book. Right? The hydrogen's gonna go over here, and the chloride, chlorine's gonna go over here. Or if other way, vice versa. Let's just say it switch places, yeah? Right? It's gonna look like that. It wouldn't matter because here this compound is still gonna look like this at the end of the day, yeah? Or it's gonna look like this, which is basically the exact same thing, but we're counting it backwards instead of forwards. So, any questions about that? Any comments? Any concerns? Okay. What is a possible pathway that could convert pentene into propanoic acid? What's a possible reaction pathway that can convert pentene into propanoic acid? Addition, then an oxidation, substitution, then an oxidation, addition and substitution, substitution and addition. What could it be? What do you guys think? A, B, C, or D? We got an A. We got another A. We got 2 A's. Maybe a B. Maybe a C. Maybe it's D. Anyone else got any suggestions of what it could be? Nope, just the 2 A's. Okay. D. What about Daniel, Nia, Blessing? What do you guys think it is? A, B, C, or D? A. What about Blessing? What do you think it is, Blessing? A. Daniel thinks it's A. Yeah, it's A. It's A. So here, first thing reaction is going to undergo is going to go a hydration addition. Remember, it can't be B or D because alkenes don't actually can't undergo substitution reactions. Yeah? Then, here, a substitution reaction simply can't form a propanoic acid. We haven't seen any substitution reactions that form a propanoic acid. So here's the hydration of propene into propan-1-ol. And then afterwards, we can have an oxidation reaction to turn propan-1-ol into propanoic acid. Does that make sense? So, Now we're gonna have a little look at this one. Right? All of you guys should remember your triglycerides. Yeah? I'm gonna. Yes, this is transesterification. Yeah? So this is transesterification over here, right? This is an OH minus catalyst. Now, I just want to tell you, like, it's like from here, you can see that here, right, the H's from this one get donated all to this to form a glycerol, yeah? And this part over here joins to this part to form our methyl ester, right? Our fatty acid methyl ester, or our biodiesel, yeah? I just want to focus a little bit on the R group. So remember there's an OH minus catalyst there. OH minus aqueous, you can also say KOH aqueous, or if you really want to, you can say NaOH aqueous. All of them are equivalent to one another, yeah? But just say OH minus aqueous, because it's just easier, yeah? I just want to fixate more on these fatty acid tails. So if I open up my best friend, chemistry data book. Google doesn't appreciate my jokes. But if I open up the chemistry data book, chem is here. Chem is the data book for 2026 is here. We'll go to the table of content. We'll go to here. And here it should have organic molecules. These are our fatty acids, yeah? Now, this part here is what we call the fatty acid tail, yeah? So basically everything besides the carboxyl group is what we call the fatty acid tail. Everything before the carboxyl group is the fatty acid tail, yeah? I just want to emphasize that. So here, right, we have all of these fatty acid tails. I want you to remember, you have to read these very carefully, because on the 2023 exam, the mistake that VCAR thought students would make, they made. They mixed up linolenic and linolenic acid, yeah? So I want you to make sure you read these very carefully to make sure you know what fatty acid tail you're looking at. And it's going to be the back end of that fatty acid tail. You made? No, I'm not made. No, I just find it funny that they mixed up linolenic and linolenic. That wasn't my exam, by the way. I'm not that old, guys. No, I didn't graduate 2023. Another one is I just want wait, who wants to try and say this for me? I'll pick someone. Cav, do you want to say that word for me?
Say that.
Yeah, say that.
I don't know. Like arachidonic.
That's
I don't
actually
know.
that's actually pretty good. It's arachnidonic. I just wanted to troll someone by saying that. Emeth, do you want to try and pronounce this?
Palmitoleic.
It's
I got that right, bro. I got that right, bro.
yeah.
Don't lie to me, bro.
Yeah. Don't worry about it. Like don't worry about the names too much. Yeah. All you need to know is you need to be able to read the name and identify the fatty acid tail. Yeah. Sometimes you might have to use the fatty acid itself. Yeah. But here you have the whole fatty acid if you need the whole fatty acid. But here I just want you to recognize that this is the fatty acid tail. That's what R represents in this diagram that I'm showing you. Yeah. So here, that's what R represents. Any questions about that? All good? Thumbs up, thumbs down. Thumbs R fatty. So is that a thumbs? I got a lot of thumbs down there. Is that all good? I actually have no idea. Okay, well Salam says thumbs up. Yeah, okay. So, which one of the following is not correct regarding the process required to produce biodiesel? Biodiesel is a mixture of fatty acid methyl esters. Glycerol is separated from biodiesel. Biodiesel is a triglyceride. The catalyst is alkaline. So which one do you guys think it is? A, B, C, or D? C, C. Everyone think it's Kerr? Guys. I mean, like C is the only one that like that doesn't really make sense. Yeah. Upon variation, I think it's C. Biodiesel is considered a because biodiesel is a fatty acid methyl ester. So that's another name we can think of it as. A mixture of these. Yeah. We do need to separate the glycerol in order to use that. Yeah. Glycerol is a waste product, so we don't want the glycerol. It is not a triglyceride. We produce it from triglycerides, but it's not a triglyceride. And here, the catalyst is in fact alkaline because it's OH minus. Good job. Dude, so now, for anyone who's done biology for you, I'm very sorry that it's a shit subject. But here we're going to be dealing with the structure of the amino acid. Yeah. Now, if I want, no, you ain't talking. Dude, stop, guys, chill out. It was like funny the first time. Oh god. These guys talking about jobs. So let me just change my screen share to my best friend. Yeah? This is my best friend, right? This is my chemistry data book. And in the chemistry data book, it has every single amino acid, right? These are referred to as alpha amino acids. Yeah? And we'll discuss this, like what the idea of the Zwitter ion is, as well as how we actually construct the amino acid and some other things that we might see with the amino acid. Yeah. So here, right, this as we see, this is our amino acid over here. Yeah. So here, this is alanine. Yeah. Here we have another one, asparagine. Yeah. Here we have another arginine, asparagine, aspartic acid, so on and so forth. And what you'll see is that all amino acids have the same fundamental backbone to them. Yeah? All of them have this exact same backbone, right? The backbone doesn't really change. Yeah? All of them have the same backbone. The only one that doesn't is maybe proline, but the VCE probably won't get you to work with proline. Yeah? But all of them have this exact same backbone. Yeah? Now, we have this group up here. This is called the R group or the Z group, depending on where you're from. Yeah? Right? The R group of the amino acid is the chain that shoots off it. Yeah? So here, the R group of asparagine is going to be that CH2, C double bond O, NH2. So that's going to be the R group of the asparagine. Does that make sense to everyone? Right? What that idea of the R group is. Because all of their backbones are the same. Yeah? All of their backbones are the same. Is that all good? Thumbs up. Give me thumbs up if that's all true. If that makes sense. So let's go back into here. So that's all okay. So let me just screen share this one again. Wait, why isn't it going full screen? So presented mode. Why is it not doing the thing I want? So here we have the amino acid. Yeah. Now the big thing that I want to look at from here is that so we have all of our amino acids here. It's now from an amino acid, what is a Zwitter ion? Yeah? And then what is how can we form a polypeptide chain? Yeah? So the first thing that we have is we want to talk about, well, what is a Zwitter ion? Yeah? If I go back into my data book, right, my best friend, a Zwitter ion is characterized as a particle, as a molecule with polar ends that has that overall the net charge of the molecule is 0. So it has polar ends, but the net charge of the molecule is 0. So I'll give you an example, right? This is alanine over here, right? But let's take alanine, and here, what I'm gonna do is this is actually what alanine would look like most of the time. Here what we see is that the alanine, right? The alanine will have a positive nitrogen, positive amine group over here, right? As well as a negative carboxylic acid group over here, yeah? So essentially, the carboxylic acid has donated its electron away, yeah? So here we have a positive end over here and a negative end over here. This is what we refer to as a Zwitter ion, right? Zwitter, spelt like this. Zwitter ion, yeah? Essentially, it's a charged molecule. Wait, it's a molecule with polar ends, but no overall net charge. Because think about it, the positive and the negative cancel out with each other, yeah? I just want you to understand that idea of the Zwitter ion. Actually, it's X. What do you mean X? Okay. Okay. But does that make sense, right? So here, right, this molecule, yeah, get this guy. Right, that's so mean. Right, down here, when we have a glycine, right, this is what its Zwitter ion is going to look like over here, yeah? That's what its Zwitter ion is going to look like over here, right? It has the polar end and the non-polar end. The big thing that you realize is I haven't actually looked at any of these like larger ones. And that's like, let's just say something like glutamic acid, which has a carboxylic acid group here. Yeah. This won't form a Zwitter ion to it. Yeah. The reason being is in a neutral solution, what's going to happen is it's going to have this 3 plus over here. Here it's going to lose the Z, and here it's going to lose the Z. So that's not a Zwitter ion. Yeah. So the H gets removed from the carboxyl group, and then it gets added to the amine group, and that creates the Zwitter ion. And the thing I'm trying to show up here is that some of these don't have Zwitter ions. So glutamic acid won't have a Zwitter ion because it will lose the H from both of these and will only gain one H plus. Same thing with glutamine, yeah? This glutamine is going to gain a H plus over here. So it's going to be H plus over here, H plus over here, because it's going to be 3 over here, and it loses 1. So that's not a Zwitter ion, yeah? Because overall this has a net charge of +1, yeah? But glycine has a net charge of 0, but it has those 2 polar ends that cancel out. So a Zwitter ion, right? No overall net charge, but polar ends that cancel each other out. Yeah? That's what a Zwitter ion is. Use this. Someone's trying to join, and I don't really want to let them join because I don't want a repeat of last time. I'm just gonna let this person join. Okay. Does that make sense? Okay. So that's the idea of the Zwitter ion, yeah? I just wanted to get that out of the way. You probably won't deal with it too much in the organic, right? Right now we're still finishing off the pathway stuff. So we haven't even finished our pathways yet, yeah? Because here, right, we have this. This is the condensation of multiple amino acids, yeah? So here we have 3 different amino acids, and what's happening is that they will lose their waters, and they'll form this amino acid, and this is called an amine link or a peptide bond. So it's either an amine linkage or a peptide bond. Yeah, this is the foundation behind what makes a polypeptide a polypeptide. Yeah, right. So this is the backbone, and as Daniel said before, this is what we characterize as a condensation polymerization, because here it's going to be like here from these two we gain 2 water molecules over here. So it's a condensation polymerization reaction that's going on here. Yeah, here it's losing these waters and it's creating a condensation. Yes, Glaze, okay, chill out. Now the big thing that I want you guys to notice is that the backbone of all of these is the exact same, right? Here the simplest backbone for this is going to be, let me see if I can find a slightly more empty page to draw on. Yeah, here the backbone of all of these ones will have the same pattern to them. Yeah, we'll have here C C double bond O N H, and we'll have here the R group over here. We'll have here, and we meant to be looking at the data. Oh wait, no, my bad, gang. I didn't even switch it. Thank you. Thanks for the call out. I didn't even notice that. So this is the thing that I was showing off before. Yeah. Here, right? So here we're breaking, like we're like taking out those waters, yeah, and we're forming this now this peptide bond. So here, for each bond we produce 1 water. Yeah, I just want you to notice that. For each bond we produce 1 water, and we'll create this backbone over here. Now, do you see how this backbone is actually the same? It has the same, like, you know, the NH, it has the C, right? There's a H over here. There's the residual group. There's the double bond O. There's then the N, and then it repeats over and over again. So you have this exact same thing going over and over again. I just want you to notice that, because sometimes what they'll do is they'll get you to draw these. So they have N, they have the H, and do you see how it's just repeating over and over again? So we start off with the N, C, C, N, C, C, and we just need to remember those like things at the top, which is going to be hydrogen, hydrogen, oxygen, hydrogen, hydrogen, oxygen, hydrogen, and we put the residual groups down the bottom. Yeah? Does that make sense? So this is just the easy way to, like, that's an easy way of drawing them, to just be able to remember that pattern over there. Yeah? The last thing I want to deal with is maybe a little bit of notation. Yeah? So what the data book has is it has, I'll go back to the data books. Make sure someone tells me to switch back over, because I might forget to switch over. Yeah? What the data book has is symbols. Yeah? So here it has alanine, arginine, asparagine, so on and so forth. Yeah? Sometimes what they'll do is that they'll write something like this. Yeah? And that means I need to form the polypeptide alanine, this tripeptide of alanine, arginine, and asparagine. Yeah? Now, here, right, if I need to draw it, I have to make sure to draw this end first. So we have the N, we have a H and the H over here, right? So because it ends with the N and H over here. Then we have here C, H, C, double bond O, N, because it's now bonding to this arginine, H, C, C, double bond O, N, N, H, C, C, double bond O, O, H, right? To represent the end of this arginine over here. Yeah? I mean, asparagine over here. So this is what the polypeptide looks like. Yeah? If I was drawing it fully. Does that make sense? That's the notation that they'll use to represent. And then obviously I need to put the residual groups on. So I've omitted the residual groups. But here it doesn't even matter. Like the residual groups don't even matter if I want to draw just the basic backbone. Now the thing I want you guys to notice is that this is called the N-terminal, And this is what we call the C terminal. Yeah, the N terminal is like the back, is the amine end of the polypeptide, and the C terminal is the carboxylic acid end of the polypeptide. So does that make sense? Give me like thumbs up, thumbs down from that. I just wanted you guys to have a decent understanding behind the polypeptides. So, thumbs up. Mine is original. So, we'll come back to here. So here, and then this is the condensation polymerization reaction. This one over here is the hydrolysis, yeah? And here, you just need to be mindful that enzymes in the body are hydrolyzing this, yeah? So they're hydrolyzing the bonds with water molecules. So here, there's two bonds, there's two peptide linkages here. So here's the first peptide linkage, and here's the second peptide linkage. What the thing is going to be doing is it's going to break the bond there, it's going to break it there, and the water molecules are going to break up so that we have these things returning back again, yeah? To hydrolyze it. So we have these waters over here, which are going to be like this, breaking up and going to their designated places. Over here. Does that make sense for everyone? Thumbs up, thumbs up. I got 2 thumbs up. I got hand clapping emojis. Anything else from anyone? No questions? Okay. Now, they've taken saccharides out of the data book. So you do not need to know a specific saccharide, yeah? They do have alpha, do have alpha glucose still in the data book, but here monosaccharides are just like those basic sugars. So they're 1 carbon sugars. And together, if we put them all together, we form polysaccharides, right? Or carbohydrates, yeah? Starch is a type of carbohydrate, and they're made up of monosaccharides, yeah? So here are the 3 that we normally see, yeah? They will have to give you galactose and fructose if they want you to use it or draw it in a question, yeah? But the big thing that you need to focus on here is the bond that's produced between, what's it called? The bond that's produced between these saccharides, yeah? So here, these monosaccharides come together and they form this disaccharide. Now you don't need to know what lactose is, but you do need to know that this bond's name is a glycosidic link or an ether link. Now, you can write both down. I chose ether link because I'm very bad at spelling. And I kept messing up the spelling of glycosidic each time I tried to spell it. Now, obviously, you guys are a lot better at spelling than I am, but at least I hope. But what you'll see here is that one of the H's from over here gets lost, and the OH group gets lost over here, and they become a water molecule. And again, this is a type of condensation reaction, right? Which means it's going to have a hydrolysis to it, yeah? So if we look at this one, this is the hydrolysis of water, yeah? And this is just an interesting, useful fact. The body can break down alpha glucose, but can't break down beta glucose, right? Which is what cellulose is made out of, or the dietary fiber that we should remember all the way back from our fuels unit, yeah? If you go all the way back to fuels, we should remember this discussion of dietary fiber and how the body can't break that down, yeah? So you don't need to know the catalyst over here. Over here in the body, you just need to know that enzymes are the thing that's breaking it down. You don't need to know the specific enzyme. I know you got someone's probably going to be like, it's actually maltase that's breaking it down, but I don't care that much about that. Yeah. So does that make sense? Can I get thumbs up, thumbs down, thumbs to the side? You know, wave your hands up and down. I don't know. Okay. What about Daniel, Blessing, Neil? You guys all thumbs up? Okay. So all you really need to know here is that they can be broken down. You don't need to know how to specifically draw them. Yeah, I know how to draw them. But all you need to know is that they have a condensation and polymerization, and that link is called a glycosidic link. Yeah. So oh yeah, this is a fun one. Here, this is a reaction responsible for producing glucose. Here they've added glycogen to the data book. And that means that I'm guessing they want you to understand that excess sugar or excess glucose in the body is converted into glycogen for storage. Yeah. Now you don't need to know the name of the process. I know the name of the process, but you don't need to know the name of the process. You just need to know that here glucose can be stored as glycogen. Yeah. And if you want to look at glycogen, we can look in our best friend, right? Our best friend has a photo of glycogen on table 20 or page 20 of the data book. There's a photo of glycogen. Yeah. If you guys want to have a look at that, just to familiarize yourself with the glycogen. Now, I'm gonna show you how to do this question. Yeah. I'm gonna ask everyone. Yeah. With 200 glucose molecules, how many glycosidic links should we form? I want to see if anyone can logic this out. Because for every two glucose molecules, we should form one glycosidic link. So how many glycosidic links should we form? Right, how many glycosidic links or ether links are formed with 200 glucoses all bonded together as a polysaccharide? If I don't get an answer, I'll pick on someone. I'll be like, you give me the answer. Mia, how many, what's it called, ether links do you think are in a polysaccharide of 200 glucose molecules?
100.
So, a little bit higher. Do you want to try and take a guess, Daniel? Or can you not talk? I don't think you can talk. Salam, what do you think? How many bonds are formed?
I thought 100, but now I think it's more. So like maybe 150.
It's 199. There's 199 ether links that are formed here. Yeah? 199 ether links that are formed. Because think about it, right? If we're joining, think about it, we have two glucoses and they're joined together with one bond. They have one glycosidic link for two glucoses, right? If we had a third glucose, right, and the third glucose is just on the end, yeah, we're going to have two glycosidic links. We put a fourth one up here. We have three glycosidic links, yeah? So here, it's just one takeaway the number of molecules that we have. So here, this also means that to form this, we actually have to produce 200 water molecules. And this is how the mass changes between these two. So here, if I calculate really quickly, this is 72 plus 12 plus 96, which is 180. So we have a molar mass of 180, yeah? So what's going to happen here is we want to find the molar mass of this polysaccharide. It's going to be 180 times by 200, because that's the number of glucoses we have in there. Take away 199 times 18, because that's the number of water molecules that we've lost here. Yeah? That's the number of water, like the mass of water that we've lost here. Does that make sense for everyone? Does that calculation make sense? All right, you must hit me with it. What's up? Unmute.
Oh, yo, I think your chat is frozen.
My chat is frozen. Oh, wait.
Yeah, because you can't see our messages.
Oh, yeah, my bad. I didn't scroll down.
Yeah, I got you.
My mic doesn't work. Oh, okay. Wait, so Daniel did say 199. But does that calculation make sense for everyone? Thumbs up, give me thumbs up, thumbs down, thumbs to the side, thumbs all around. Forgive. Bro, I'm not that old. I'm the same age as you guys. I swear. I swear on God, bro. On God. Oh, and oh yeah, this one should have been way earlier. So we remember the height. So transesterification is the well, it's not. It's technically not a hydrolysis. So technically, transesterification isn't a hydrolysis because it doesn't use water. Yeah, it's still a but there's a condensation reaction that goes with it. Yeah, so here the condensation reaction. Oh wait. Sorry. Okay, I'm looking at a different reaction. That's why I'm like tripping out here. This one is slightly different because this isn't a fatty. This isn't a biodiesel. This isn't a fatty acid methyl ester. Yeah, this is a fatty acid, right? So fatty acid reacting with a glycerol produces a triglyceride, right? Plus 3 water molecules. So here what you can see is that these 3 waters are getting lost, right? Only 60. These 3 water molecules will be lost. And what's going to happen is that these 2 ends just join up with one another to form this ester functional group, aka our triglyceride, right? And here what we see is that, well, of course, with a condensation, we have a hydrolysis to go with that one. Now, you do not need to know the catalyst of this one. You just need to know how this one works. Does that make sense for everyone? Thumbs up, thumbs down, thumbs to the side, thumbs all around. What's up? Emeth, what's your query? Hit me with it. Say the last bit. So here we see the water molecule. So we see that here the glycerol is losing its H's, the fatty acid is losing its OH group, and they're combining together to form this triglyceride here, right? So they're coming together, right? All of these parts are coming together, and they're forming the triglyceride, and this is losing the water molecule over here. Any questions about that? So the CH3 don't change. No, there's no CH3s here. It's just, yeah, so this backbone doesn't change at all. It's the glycerol backbone that we use for the triglyceride. Does that make sense? Any questions, comments, concerns? Okay. And then obviously here we have the hydrolysis, which is just the reverse version of it. Yeah? So, which statement correctly applies to triglyceride? Water is produced when they are broken down. Their hydrolysis involves enzymes. They are reduced to produce energy. They are stored as glucose when in excess. So what do you guys think? So what do you guys think? A, B, C, or D? B. Okay, so you might say B. Anyone else picking B? B as well. What enzyme hydrolysis? No. So the enzyme's the catalyst. Yeah, the enzyme's the catalyst that causes the hydrolysis. So here the answer is B, right? The enzyme is what causes the hydrolysis. Here this is wrong because It's not produced when it's broken down, right? C is wrong because they aren't reduced to produce energy. They'll be oxidized to produce energy, if anything. And then D, they're stored as glucose. No, this is a fat compared to a saccharide. So, what functional group is formed in the reaction of 3 fatty acid molecules and glycerol? What's the functional group form? What do you guys think? A, B, C, or D? Have D. We get another D. Any more D's? Any more D all around? Get D from Daniel. Anyone else? Cav, Mia, Blessing. What do you guys think? D, D, and D. I'll leave your thoughts. So yeah, it's D. Yeah, okay. And here, this question's just straight wrong. It's meant to be 2 OH groups that form the glycosidic link. Don't worry about this one. But here are a bunch of questions you can practice. I'm gonna post this one's posted up on my website already. If you guys want links to that website, send me a message and I will give you the website. Yeah, or I'll just put the link to the website in the chat now. Let me just put it in the chat now. Any depths here? So this part just deals with more or less the sustainability. Now, I'm going to say this now. The sustainability part is mostly just YAP. I'm going to say this now. It's very much just YAP. But the whole idea is more or less focusing on how can we make these things more sustainable. So remember, sustainability is it needs to be produced at a rate greater than or equal to consumption without impacting future generations. Yeah? And we're just discussing that with, potentially calculations and the idea of the circular economy and obviously the green principles. Yeah. So here are some more definitions, right? If you guys want to have a read over them. None of these are too crazy. Maybe feedstocks just helps you understand what the hell they're actually talking about when they talk about a feedstock. And a renewable resource, that's a second definition. So I've said a first definition can be produced at a rate greater than or equal to consumption. Yeah, feedstock up here. Feedstock. So it's just the raw material used to produce another product, right? It's like, I use iron ore to produce iron. So iron ore is the feedstock there. Or like to produce like sugar, I use sugar cane. So sugar cane is the feedstock there. So now there's some ways we refer to efficiency. The first one is through atom economy, right? This is an atom economy calculation here, yeah? And essentially, right, what it does is it calculates the mass that we've gotten, the mass of the desired product. So here the desired product is ethyl propanoate, yeah? And then compares that to a ratio with the reactants that you use, or the molar mass of the reactants that you use. So the total molar mass of the reactants is going to be 120, yeah? So this is our desired product divided by the total number of moles of our reactants. And here we see this reaction has an 85% atom economy, right? So that's what atom economy refers to. It's just the, what's it called? The ratio of the mass of the desired product compared to the mass of the reactants. Is there any questions about that? Any comments? Any concerns? Give me thumbs up, thumbs down. Okay. So here, now we deal with the idea. I have a concern. What's up? Unmute yourself. Oh wait, never mind. Wait, go on, Daniel. What's up? It's fine. Okay. I'll talk to you about it after if you need me to. But here it says during a combustion. So this here is a percentage yield question. Yeah. Now don't mix up percentage yield and atom economy. They're not the same thing. Yeah. Percentage yield is how much is actually produced. So here we have propene. Let me grab out my calculator. I put them on my desk. So I'm gonna grab out my calculator for this. So here, right? If we want to find out the percentage yield of this, right? We most likely just want to find out the percentage yield of the carbon dioxide. So we want to find the percentage yield of the carbon dioxide here. Yeah. So here, what we can do is we can find the number of moles of propene. So here that is going to be 36 plus 6, which is just going to be divided by 42, which is equal to 2.14 blah blah blah. So that's the number of moles that we produce. Then we times this by 3, right? Because the molar ratio is a 2 to 6 or a 1 to 3 ratio, so we can multiply it by 3 over 1 to get those number of moles. Now I wouldn't do this as my actual working out here, yeah, but because this is because I don't have any space, I'm just gonna do it like this, yeah. So we can times this by 3, and we get 6.44 moles of carbon dioxide should be produced, yeah. Then we're going to times this by the molar mass of carbon dioxide. So here we should produce 800.485 grams of carbon dioxide here, yeah. But we're only producing 110. And here to find the percentage yield of this, what we're going to do is we're going to do 210.4 divided by 283.485. This is the actual divided by the theoretical amount. And then we're going to see what we get as our final answer. So we get here, which is 0.742 or 74.2%. Yeah. Now, if you don't know that formula, that's fine. Yeah. You don't need to know that formula. It's in your data book. It's in your best friend. So remember, as long as you remember what's in your best friend, maybe don't phrase it like that. Fuck it. If you know what's in your best friend, right, you should be good. It's in the formula section. In the formula section, it should have a thing for percentage yield. So this is the actual amount that we produce, and this is the theoretical amount that we produce. Yeah. So we're doing the actual divided by the theoretical, and this is the percentage yield of this. And this sort of helps us to understand, well, how efficient is this calculation? Yeah. Is that all good? Or how efficient is this reaction? Does anyone have any questions? Thumbs up, thumbs down, thumbs to the side, thumbs all around. What are we feeling here? Okay. So, I get it. Now, these are just some reasons that we might not have 100% yield. Now, I can read through all of these and explain them all, but they're very self-explanatory. Like, you know, if reactants and products are lost, obviously we're not going to get like 100% yield, yeah? If it's an equilibrium reaction, it won't go to completion. Like, some of you guys haven't dealt with this equilibrium idea, yeah? But once you do, it'll make a lot more sense why we don't get an 100% yield there. Like, the reaction is too slow. If it's too slow, right, after 10 minutes, I measure it, the reaction hasn't even gone to completion yet. So I'm basically measuring nothing. If there's impurities, right, impurities mean we're measuring a mass that could be greater than the actual mass that we have. So that causes our percentage yield to not be 100%. So overall, these are just some of the reasons why we won't have a 100% percentage yield. And I just want to go back to this idea of the efficiency. Why are we talking about this? Yeah, it's because we want these are ways to measure the efficiency of our process, and thereby will help us understand how sustainable of a process it is. Yeah, because if we're like producing like a 1% atom economy, right, of this really good product, then like, you know, who cares about the product? There's only 1% atom economy. Yeah, if we're only producing 1% yield of a product, well, what's the point of that product? Yeah, they're just measures on that sustainability. Yeah. Now they have this formula. Essentially, with a multi-step, if they want you to find the multi-step percentage yield, you just multiply all of these together to one another. So again, you have a calculator, so it's going to be 0.8 times 0.6 times 0.9, and that's going to be the overall percentage yield of the pathway, yeah? In terms of atom economy, is a lower value better? No, we want the value to be as close to 1 or 100% as possible, right? A higher value is better because a higher value means that we're more likely to produce our desired product. Does that idea of percentage yield make sense? The overall percentage yield? It's just that we're multiplying all of our steps together, yeah? To get that overall percentage yield. Thumbs up, thumbs down, thumbs aside, thumbs all around. So here, what is the total overall percentage yield of the following reaction pathway? What do you guys think? A, B, C, or D? A. Salam says A. Anyone else say A? Emeth says D. Blessing says A. D. A's, we got D's. Emeth, can you explain why you chose D? I guess. The answer is A. Because it's going to be the 0.8 times 0.7, which is equal to 0.56. Yeah? Remember, you have a calculator for this, so you don't have to do it in your head. But I can do it in my head. Math. I'll let you do... I'll come back to this one, yeah? I just want to deal with this idea of, renewable feedstock, yeah? A renewable feedstock means that we can obtain a renewable resource at a rate greater than or equal to consumption, yeah? Now, this is just an example. The reason I've shown you this example here, essentially the idea is that we can produce lactic acid, right, very easily. And essentially, this allows us to create polymer polylactic acid. You don't need to know this compound itself, right? This just is meant to help with your understanding. But the whole point of this is more or less, well, here, polymer polylactic acid can be used as a bioplastic or a biodegradable plastic in our society, yeah? And it more or less, like, it means that we can produce plastics more renewably, yeah? Oh, what? Okay. This was gonna go over like the... No, it's not here. No, it's not that one. Where's the thing I want? Let me just open this. Let me just find it real quick. Chemistry. It's meant to be here. It's not there. There's a thing that's meant to be there. It's not there. I was like working on these last night, and it's not here. But it's a full table, man. There's a reason I'm not drawing. It's not in the data book. So I'll screen share this part real quick. Yeah. You don't need to know these ones as well. Yeah. It's more or less just explaining how it's okay, Uncle. You know you forget things sometimes. Okay, bro. Okay. I'm just getting all the smoke today, aren't I? But I'm going to show this one off to you, yeah? And the reason I'm showing this one off to you guys is more or less it helps you understand and the considerations behind like different fuels, yeah, and how they're getting better and better all the time, yeah. Right. So what I ultimately want to focus on here is that all of these impacts here, the considerations are what we're talking about when we talk about sustainability. So having a good grasp and a good understanding behind these ideas, like here, displacement of food and crops and deforestation, competes with valuable food resources. Those negatively impact future generations. Yeah. Here, like with the lot with the it's a valid again. When you look at that, when you look at that 5 to 6 mark on the back of your exam, you're gonna be like, thank God we dealt with sustainability. Yeah. But the whole idea is to focus on how do these improve the sustainability, right? How do these improve the renewability as well as reduce the impact on future generations, right? Reduce the impact on food scarcity, land use, input versus output, deforestation, climate change, pollution. How does it deal with all of these things? And how do these biofuels help to rectify the issues of past biofuels? So the idea of the first, second, third, and fourth is more or less, you don't need to know them, you just need to understand the idea of how they're improving and how they help to improve the sustainability of a process. Yeah? So I'll come back to here, right? And we'll come back to this one. It's just explain the advantages of the first and third. You don't the third and the fourth. You don't need to know the third and the fourth generation. You just need to understand how they the ideas of the improving of those third and fourth and how they're making it more sustainable in terms of the renewability and impact on the future generations. Yeah. So here, the majority of plastics currently used in our society are. What do you think the majority of plastics currently used in our society are? Are they A, B, C, or D? And I'm just going to say currently used. Yeah? So what do you guys think? A, B, C, or D? No one's got any ideas? What's up, Salam?
I think it might be frozen again because some of us put answers.
Okay. It's because I need to scroll down. Yeah, it's because I'm getting older, isn't it?
Yeah, it is.
Yeah, it's A. Wait. Okay, well that. Oh yeah. Then it says here. Yeah, glad you. Biofuels continue to develop. The generation that is the least sustainable is it the first generation, second, third, or fourth generation? Yeah? It's D. It's the fourth generation. That's the least sustainable. As we go up in generation, does it improve in sustainability? Here it's A, yeah? The fourth generation are the most sustainable. The third generation are the least sustainable ones, yeah? So as the generation goes up and up and up, it gets more and more sustainable, yeah? Yeah, I'm gonna have to create like a polling option or something because I want you guys copying off each other. Oh yeah. This one is just sort of going through the idea of the catalyst and how that can improve the sustainability. Essentially, a catalyst can here the catalyst can be used to allow for us to produce, let's just say, better byproducts. So here we'll produce sulfur or we'll produce hydrogen sulfur. Wait, hydrogen sulfur. I'm pretty sure. Yeah. We don't want to produce that. So before we would just have the crude oil with the sulfur and we'd allow the sulfur to go in the air. Instead, what we're doing is that we're refining this process by using a series of catalysts in order to reuse that sulfur, right? Which goes back into this idea of the circular economy, right? we're not just wasting that sulfur, we're actually reusing it for something else. Yeah? And catalysts now allow us to do that because it allows for alternative pathways to occur, for us to create these byproducts. Does that make sense? Thumbs up, thumbs down. These are just all the ways that we can improve. We use catalysts to improve. They're all, again, pretty self-explanatory. And will that make use right about, say the end? What? Be sure that won't be too hard. Where's that they meant to go? Wait, can you add the whole question again? Yes, it's in the study design. Yeah, so they'll get you to they'll just get you to discuss the idea of how a catalyst can improve it. They don't want you to understand this. They don't need you to know the specific pathway of how the catalyst works. You just need you to know that these are ways that catalysts can improve it. So improve the selectivity, right? It just means that we remove unwanted byproducts, lower energy consumption. Remember, the catalyst lowers the activation energy. It's renewable resources. So here, catalysts can be used to facilitate. Yeah, essentially, catalysts can help us reduce the requirement on our use on renewable resources. Yeah, catalysts can create safer reactions because we don't have to run them at such high temperatures. Yeah. In alignment with the green chem principles. Yes, this is in alignment. So it's in alignment with the green chem principle catalysts, right? So here, catalysts increase the rate of reaction at which products are formed. The benefit of the use of catalysts to achieve this increase in rate is a safer reaction, improved yield, lower energy consumption, better selectivity. What do you guys think? What do you think is the main benefit? So I've got one C, with another C. C. Yep. So here it's C. The main thing a catalyst does is it speeds up the rate of reaction. It will improve the yield by not that much. And in VCE chemistry, we just think about it as it only impacts the rate and not the yield of a reaction. Yeah. Obviously, I know many of you guys haven't done rates in equilibrium, but that's how a catalyst comes in. Yeah. With design for safety, essentially, you want to produce safe products. Yeah. So this process here describes how here, right, we can turn this plastic, right? This is a plastic. A polymer is a plastic. This plastic into safer products to release into the environment. Yeah. That's all this is talking about here. Now, you don't need to know the specific polymer. Energy consumption is the same as the activation energy, right? Yeah, basically. So reducing the energy reducing the activation energy also helps us reduce the energy consumption. So the whole idea is that we produce things that we can release back into the environment. Yeah, that's what safer products means. Here's this really cool thing about sustainability of seaweed that I saw. I thought it was interesting. But essentially, these go back into our dot points of like sustainability. Remember, land use, food versus fuel, input versus output. Like here, they talk about pollution. So here they talk about biodegradability. This means it reduces the pollution, right? We can also talk about how it reduces the carbon emissions. And here it says production of oxygen by consuming carbon dioxide. Again, reduce the effect of climate change, and deforestation as well, right? Because here, seaweed is underwater. It's not destroying like immense amount of natural habitats, yeah, and it can be produced very quickly. So that's like, again, this, like, these last things are more or less to make sure to give you ideas or generate ideas for our sustainability discussion on the exam. So I'll just do this one. So what do you guys think the answer is? Biodegradable materials are recyclable, can take hundreds of years to break down, always break down into non-toxic products, are made of polymers that can, I've seen 1B, are made of polymers that can break down into monosaccharides or amino acids. Pretty good. So here, C is the best answer. If it was non-biodegradable, then it would take hundreds of years to form. Yeah? But because it's biodegradable, it only takes a short amount of time to break down. Yeah? And then I'll come back to this one here. I just want to explain this. So, first, what do you guys think has the lowest atom economy here? What do you guys think has the lowest atom economy? Any ideas? Any thoughts? Saying C. Are humans biodegradable? Just one. I mean, I guess if you try hard enough, they are. If the data book is you power, what are you without? Okay. So I can see. So we've got a variety of answers. I've seen one person say C, one person say D, and one person say A. Yeah. So, and this is the last thing that we'll do, and then I'll let you guys go. But here with this one, this has an atom economy of 100%. Yeah. Because we only produce the desired product. Yeah. So that means it has an atom economy of 100%. This one over here, right? This is atom economy over here. This is 180. This one over here is going to be 40, like 24, 46. So we produce 92 here because we have two of them. Yeah. So here it's 92 divided by 180, which is approximately something like 50%. Yeah. This one down here, this one we know has atom economy of 46. On this has the desired product has a molar mass of 46. Over here we get 40 plus what is this? CH 24, 24, 29, 29, 30, 29 plus 35, 5, which is 64.5. So we have a 64.5 plus 40. We have a 46 divided by this, and we get here 44%. Yeah. And this one down here, we can just do the exact same process. We get 46. Here we have 14, 32, 46, 47. Yeah. This one here has a 16, 29, 16, which is 45. So we have a 40. So this one's molar mass is 45. We do 45 plus 47. So 45 plus 47. Which is, typical kind of MCQ. So 92 and 46. So if we do 46 divided by 92, yeah, so 46 divided by 92, we get exactly 15%. So we get C, yeah? So the atom economy is all of the reactants on product. This is all of the reactants on the products, yeah? And it's not just all of the products, it's the desired product, yeah? So the desired product, they'll make sure they outline in the question. So that is today's class, yeah?